Hello, my name is Matteo Meneghini, and I'm going to introduce the basic concepts and use of LTspice, which is a very powerful circuit simulator that can be used in many microelectronic studies. Most of the materials I am mentioning is coming basically from the analog.com website. So here you can find also further information. You can use this website as a reference if you're going to find and look for further information about LTspice. So the point is that if you have already studied about electronics, you know that in principle with the textbook you can get to know many first order textbook like equations that give an approximate indication of the current voltage behavior of electronic components. And they are very important and suitable for quick calculations. So you have done maybe in the classroom several exercises by using this kind of equations. And this is an example, the equation of a MOSFET that can effectively reproduce the main current voltage relation. So the main relation between the voltages which are applied to the gate and to the drain and the current which is flowing through the device through some very important parameters which are related to the geometry and the properties of the materials and devices. Now, the point is that by using these relatively simple equations, we can reproduce the behavior of the circuits, but maybe we are not really able to describe all effects related to, for instance, temperatures, high field, parasitic capacitances that might be present in the device structure, short channel effects, channel length modulation, and so on and so forth. And in addition, in several cases, if we are dealing with very complex circuits, this study might require the use of suitable softwares. So the main goal of simulation is to offer advantages. Since simulation basically allows you to study circuit operation beyond the first order models that are studied in the classroom. And specifically, a circuit simulator allows to evaluate even on complex circuits the DC performance, the transient behavior, the AC response, the temperature behavior, and so on and so forth. Obviously, a simulator uses equations and it uses mathematical models, which are basically there to replicate the operation of realistic electronic components, including the simple resistors, inductors, and capacitors, but obviously also the nonlinear behavior of transistors, op amps, diodes, and so on and so forth. So after, and only after a study based on textbook formulas, which is necessary, simulation allows the students and designers to verify the performance of the circuits before reaching the prototyping phase. So obviously we have a warning here. So circuit simulation does not replace the study of circuits and basically the basic knowledge on the design of circuits. Simulation is a powerful tool you can use after you have understood how a circuit works in order to try to optimize second order parameters. So keep that in mind. It is not replacing the study of circuits, definitely. And in this lecture, basically, we're going to start introducing the LTspice, which is a circuit simulator, which has been developed and is maintained by Analog Devices, and which is free in many cases. So the point is that LTspice is a high performance simulator software which allows you basically, first of all, to capture the schematic of a circuit and also to basically apply some specific signal to your circuit in order to be able to evaluate the evolution as a function of time or as a function of any input parameter of the output signal of your circuit. So obviously included in the download of LTspice, you can find macro models for a majority of analog devices, switching regulators, amplifiers, and a library of devices for general circuit simulation. So these are aspects you need to consider once you want to approach this relatively powerful tool. So the goal now of this set of lectures is to basically have a look on how effectively the simulator can be used and to give you some practical advice which can be very useful for developing your own projects and evaluating the behavior of the circuits and devices you're using. So a first question might be how to get this LTspice software. So it's relatively easy. Here you can find the link that you need to click on. And if you look at the link, basically you can find the LTspice page on the Analog Devices website. And of course, you have the download links, for instance, for Windows and for Mac. But at the same time, you might find here a lot of documentation that might be useful for developing your own projects and for understanding how the tool works. Now, the goal of this specific set of tutorials is to try to get to get a hands-on knowledge, basically that allows you to try using the simulator for simple projects. So what you see here is typically the window that is opened once you open the LTspice software. You see that as all the softwares that you might already know, there are several tabs here: File, Edit, Hierarchy, View, Simulate, Tools, Window, and Help that allow you to access the main functions of the software. And of course, you have some quick access button that you can create here if you want to create, for instance, a new schematic, or to open a project, or to save a project, and so on and so forth. So we are going now to give a look to the main input commands that might be useful here, so that you can get a feeling of what are the main characteristics of the software and how you can basically create a circuit and start the simulation of a circuit. The first thing we want to know is how to basically add components to the circuit, and also basically to change the properties of the individual components. So for instance, we will start with a very simple circuit, which is a 4-resistor network in which we place a transistor. So it's basically a transistor biased by a 4-resistor network, which is quite easy. So basically what you see here is that we have some buttons here for adding a resistor, for instance, a capacitor, a inductor, diode, and so on and so forth. And we're going to use those buttons in order to create our simple circuit. Let's start adding a resistor. So you see, if I click on the button with the sign of the resistor, this kind of symbol, which is the typical symbol of the resistor, appears. And of course, if I scroll in and out with my mouse, you see that the size, the level of zoom basically is changing. So if I move it around, I can then choose the position where to put it. And obviously, since I don't have any specific position in mind, because it's the first component I add, I just click on the mouse so that it gets fixed in that position. Once I click with the mouse, a second resistor appears. Now, what I can decide is whether to click on the escape key. So basically, it disappears and I can start again. Or the other opportunity would have been to add the second resistor to a specific position in my circuit. Say we want to add a second resistor. Well, I can definitely, if it is basically a network of resistors that is biasing, for instance, bipolar transistor, I can add a resistor here, R2, and then I can decide adding another resistor here, R3, and adding another resistor here. Note that in principle, I can also rotate and mirror my components. So in this example, for instance, I want the resistor in this specific position, but if I press the button Ctrl R, basically I can rotate, you can see it here, my resistor, so that it appears horizontal or vertical in this case. And this is quite convenient if you want. There is also another key combination, which is Ctrl E, that allows you basically to mirror the transistor if you want. Now, of course, I have now added a couple of components that I don't want to have there. So if I want to delete them, I have an opportunity of clicking on this cut key. I click there, cut button, you see the scissors appearing, and I can now, by clicking on the left button of the mouse, basically select the region of the schematic I want to delete. And once I release the button of the mouse, everything is deleted. Of course, now my scissors are still there. If I want, I can use them again to delete another component. Otherwise, I can press the key, the button escape on the keyboard, and then I leave the scissors down. So I remember I wanted to draw 4 resistors, and so I'm putting a second resistor here, a third resistor there, sorry, and a fourth resistor here. And then I press escape, so I can basically have my 4 resistors network. Now, the point is that I want to add a transistor, and of course, I have the opportunity of doing so. There is no button here for adding a transistor, so I will have to press this button, component, which will allow me to access the library of components which are available in LTspice. So you see, it's a very large library. And in principle, once I basically open this library, you see I have many components: ADCs, comparators, DACs, op-amps, and so on and so forth. And I will look for instance, an NPN bipolar transistor, which is what I want to add to this schematic. So you see here, I can add an NPN transistor. You see already, if I click here, I can already see the symbol of the transistor. And I click on OK, and now I can add my NPN transistor Q1, which I might want to add at some specific position in the circuit, like for instance here. Of course, once I click on the mouse, I see I have the opportunity of adding a second transistor, but then obviously I don't want to add it, so I press Escape. Now, of course, I might realize that it's not really nice to have the components in these specific locations, and this is exactly what I wanted to do. So you see here I have two buttons, Move and Drag. I will now click on the button Move, so this little hand will come out. And now I have to decide what I want to move. So for instance, say I want to move the resistor R3. I want to move the resistor R3 rightwards, for instance, here. And I want to move the resistor R4 more or less in the same position. So I will basically select my resistor and move it in the position where I want it to be. Now I realize that if I want to have an ordered schematic, I need to move a little bit the components around, and this is exactly what I'm doing by using this hand in order to basically, for instance, find a way to have the components exactly matching the the positions where I want them to be. So say that in this way, you might have seen that I have already connected electrically the resistor R4 with the transistor, as you can see over here. And I have done it because I have overlapped basically the small pin, which is this little square of the resistor, with a little square, which is representing the contact, in this case of the base, for instance, of the transistor. And if you put one on top of the other, you create already an electrical connection. This is one way of creating electrical connections. Another way, of course, is to use the wire button that you have here. And you can have the very same function if you press the button F3 on the keyboard. So say I click on the wire button, you see that now this thing is appearing, this cross, which basically allows me to align the position of the contacts and understand where the wire is going to end if I start. Now, I still have to click on my mouse. If I move the mouse around, you see that basically I can change the view, but this is not what I want to do. So basically, I will prefer to have it centered, right? Similar to what I have now. And then I click on this terminal, and you see that I can start wiring, and I connect electrically this terminal of the resistor R1, for instance, this terminal of the resistor R3. And once I reach a connection, basically I click, and you see that the terminal is disappearing and only the wire is left, which is blue in this drawing. Of course, I can do the same for this terminal to be connected with this other terminal. Every time I click, I place a wire, and after I click the second time, the wire is drawn. Of course, I want this node here in the middle between the two resistors to be connected to the base of the transistor. So I just create an electrical connection here so that the middle node between the two resistors, the intermediate node, is connected to the base. And then, of course, I'm going to draw an electrical connection between these two terminals here that you can see here. And now, of course, this is a 4-resistor network. So in principle, I have already made all my electrical connections, and I can press the escape key on the keyboard. So now my circuit is drawn, but of course, I still have to choose the values of the resistors, for instance, and the system, and also the names if I want. Say I want to change the name, I would have to right-click on the name of the resistor here. If I right-click here, you see I have an opportunity to change the name of the resistor. For now, I am happy with the name R1, so I don't need to change it. I can press this button here to have a vertical text if I want, and also I can change, if I want, the size of the text. For the moment, I am happy with 1.5, which is the default size, but in many cases, the text might become crowded, and I might want to reduce the font size in order to make it more readable. In this case, I don't need to do it, so I can really continue in this way. So let me choose OK, but remember, I could have changed the name of the resistor by typing here something different than R1. If I do the same on R, I can change the value of the resistor. So here, for instance, I might want to put a value, for instance, of 10 kilo ohm, and I just type 10K there if I want to use 10 kilo ohm. Remember other possible values. Of course, I could have written just um, 10,000, and that would have given me the same result. If I write 10 M, this is 10 milliohm. And please consider and remind that if I want to make 10 mega ohm resistor, it's not sufficient to write 10 M. I would need to write 10 meg, because basically this allows me to distinguish between the million, which is M, and 10 mega ohm, which is 10 meg. Keep that in mind if you need to use such high values of resistance. So now the value I wanted to put was 10 kilo ohm, and this is exactly what I want to put there. You see that it appears on the schematic. In the same way, I can add an additional value here. Say I want to have kind of a symmetric network, so I use 10 kilo ohm also here. And of course, now we've placed these two values of my resistor. So now I can choose the value of the resistor R3, which I might want to put at 470 ohm, just to put the number over there. And this resistor R4 can be put at the value 220, so that I have chosen the values of the resistors of my network. Of course, now my transistor is a generic transistor. You see, if I go here, it's just CQ1, which is the typical name of transistor, NPN. But if I right-click here, you see I have some options menu, and I can click here on the Pick New Transistor. So if I want to choose a specific model, I can just click here, and basically a list of transistors appears. You see I have many of them. And I have also summary of the main characteristics, especially the maximum voltage I can apply to the transistor until the maximum collector current. So just to put a realistic transistor, which is kind of common, I put this transistor, which is the 2N2222, which in this case is manufactured by NXP, and you can basically find a lot of them also with different manufacturers. So let's say I choose this one, I click OK, and I see the name of the transistor appearing, which is kind of convenient in the case you want to test your circuit also with real components. And this is kind of a very common transistor, which is found in many laboratories. So now we have the schematic of the circuit, but of course, as every circuit, there is something missing, right? And we need to add a power supply if you want to supply a certain voltage and current to the circuit to be able for the circuit to operate. So once again, in order to add a power supply, we will click here on component, and we will look for this voltage. You see here, you have already the symbol of the power supply, voltage supply. So if I click here, of course, I would have also a current generator here if I wanted to, but in our case, we want to apply a voltage. So for instance, I will put this here. It's called the voltage supply V1. And then if I press F3 or if I click here on this wire button, I can connect electrically the voltage generator to my circuit, positive and negative terminal, as you see over here. So we have not completed yet. Of course, we want to choose the voltage and the name of the supply. Let me choose just the voltage here. I'm going to choose, for instance, 6, which is 6 volt. And most of the students think they have done everything at this point and they can start simulating. But there is one very important thing which is missing, which is a voltage reference. And typically our simulator, also in reality, you want to know basically what's the 0 volt reference for your circuit. And you can do that by adding a ground. You see here, I click here, ground to your circuit. So basically, this is my ground reference, the 0 volt for my circuit, and I need to electrical connect that to a terminal in the circuit, a node basically in the circuit. What I do is basically to use the negative supply and to connect that to 0. So I have 0 volt here, the ground potential, and 6 volt on the other terminal. But basically, this is a choice I make because I want that to be my potential reference. Important thing is that every circuit has a reference. Even if you measure with an oscilloscope one of the two terminals on the probe is connected to ground, right? And this is exactly what you want to do here in the circuit to make sure you have a unique voltage reference. At this point, we are ready to start simulating our circuit. And of course, the first thing we want to know is what is the DC operating point of the circuit. Of course, once we apply our bias here, current will start flowing through these two resistors, and these two resistors will bring a certain voltage here to the base of the transistor, and a certain current, the transistor will be likely on, if I have drawn and made things in a proper way. So some current will start flowing also through the collector and the transistor and the emitter, and therefore a specific voltage will appear on the base of the transistor, between base and emitter, and of course a certain current will start flowing. And we want to know what's the DC operating bias point. So that's going to be the first simulation we're going to make. So if I click on simulate here, you see, I cannot really run a simulator because I still have to tell the simulator what is the simulation I want to run, and I can want to click on edit simulation command. Here you see a menu appears where I can fill some and put some instruction for transient simulation, AC analysis, DC sweep, noise analysis, DC transfer, and DC operating point. Of course, the first thing I want to make, exactly as I was mentioning, is to calculate what is going to be the DC operating point of my circuit. And if I click here on DC operating point, you see I have a summary. This is going to compute the DC operating point, treating capacitances as open circuits and inductances as short circuit. This is a syntax, which is .op, and that syntax is going to be used by the simulator. Remember, what I am teaching you now is the graphical environment where basically you can use this graphical interface in order to create circuit and simulate. But everything at simulator levels is done with kind of a text-like instruction set, where basically every instruction has a specific syntax. In this case, for calculating the DC operating point, the syntax is .op. So if I click OK, I will see that syntax appearing here. And at this point, I am ready basically to start using the circuit and simulating its properties. So now I can go here and click on Simulate Run. You see here the man running. I could also click here on this button, Run. If I do so, you see, in this case, it's a very simple simulation. This output comes out. You can clearly see here that I have different nodes which are identified in my circuit. Node 1, node 2, and so on and so forth. If you pay attention here, if I go on this node, and you give a look to the bottom left of the screen, you see there is written, this is node N001. The DC operating point of the node 001 is 6 volt. So now each node has a name, N001, in this case it's going to be N002, and the DC operating point is 2.6 volt, and so on and so forth. So basically the simulator considers my circuit to be composed by several nodes, as is kind of obvious basically. And if I click once again on Run, it's going to give me the voltage on each node. 6 volt for the node 001, which is this node here, 2.6 volt for the node 002, which is the base of the transistor, and so on and so forth. The output is also going to give me, for instance, the value of the currents, for instance, through the various resistors, current to the resistor R4, R3, and current through the resistor R2 and R1. And of course, I have also the current flowing through the collector, the base, and the emitter terminal of the transistor. Let's give a look to the number just to have a feeling of what we're talking about. So first of all, we have 6 volts between basically the power supply and ground. And we see that at the base terminal, we have 2.6 volt, which is kind of reasonable. It's, you see, it's not exactly half of the voltage, even if here I have a voltage divider with two identical resistors. And the point is that I have some of the current which is flowing through the base of the transistor, and that's going definitely to subtract some current to the two resistors. So the current through the resistor R1 is around 0.3 milliamps, the current through the resistor R2 is lower, is simply 0.26 milliamps because some of the current is flowing through the base, which is here 7.9 10 to the power minus 5 amps. So that's going to be the Kirchhoff law of this node over here. The other thing we notice is that basically, if we click on the nodes, once again, we can see the voltages. And we can see that there is a certain difference of potential between, for instance, the emitter here, 1.88 volt, and the base of the transistor, 2.6 volt. So if I click on this node and I keep pressed, you see that a voltage probe is appearing. And if I move the mouse while clicking, for instance, to the emitter terminal, I see now I can release the mouse and a differential voltage probe is put in place. So that's going to give me the difference in voltage between, if you give a look to the bottom left of the screen, between the voltage of the node N002 and P002. Let me release the button, and you see that a voltage is appearing here, a voltage reading, 0.7 volt, basically. And of course, you can see that's the typical base emitter voltage drop for a transistor which is turned on in the forward active region. So you see that not only we have a way of accessing the voltage on a node just by going on the node, but we can also create a differential probe, as we have just done, in order to measure the difference between voltage at two specific nodes. In this case, reading the base emitter voltage of the transistor in a quite accurate way. In the same way, you see, if I basically click on a resistor, I have approach a resistor, I hover with the mouse on a resistor, and give a look to what is on the bottom of the screen, you see that I have the DC operating point of the resistor. I can see, for instance, the current flowing there, which is 8.49 milliamps. And also you have a calculation of the power dissipation, which is for a resistor is simply the product of voltage times the current, of course, or Ra squared, which is 33 milliwatts in this case, approximately. So you see that we already have a simple way of collecting information on the DC operating bias point of my circuit. So now in the next tutorial, we will start looking at the time-dependent analysis of very simple circuits in order to build basically our knowledge on how to effectively and successfully use LTspice as a circuit simulator.